Joule, from Wikipedia, the free encyclopedia, at en.wikipedia.org. The joule is the unit of energy in the International System of Units, SI. It is equal to the amount of work done when a force of 1 Newton displaces a mass through a distance of 1 meter in the direction of that force. It is also the energy dissipated as heat when an electric current of 1 ampere passes through a resistance of 1 ohm for 1 second. It is named after the English physicist James Prescott Joule. Definition. In terms of SI base units and in terms of SI derived units with special names, the joule is defined as kilograms times meters squared per second squared, or newtons times meters, or pascals times meters cubed, or watts times seconds, or coulombs times volts. 1 joule can also be defined by any of the following. The work required to move an electric charge of 1 coulomb through an electric potential difference of 1 volt, or 1 coulomb volt. This relationship can be used to define the volt. The work required to produce 1 watt of power for 1 second, or 1 watt second. This relationship can be used to define the watt. The joule is named after James Prescott Joule. As with every SI unit named for a person, its symbol starts with an uppercase letter, but when written in full, it follows the rules for capitalization of a common noun, i.e. joule becomes capitalized at the beginning of a sentence and in titles, but is otherwise in lowercase. History. The CGS system had been declared official in 1881 at the First International Electrical Congress. The erg was adopted as its unit of energy in 1882. Wilhelm Siemens, in his inauguration speech as chairman of the British Association for the Advancement of Science, first proposed the joule as unit of heat to be derived from the electromagnetic units ampere and ohm in CGS units equivalent to 10 to the 7th erg. The naming of the unit in honor of James Prescott Joule, at the time retired but still living, age 63, is due to Siemens. Quote, "Such a heat unit, if found acceptable, might with great propriety, I think, be called the joule, after the man who has done so much to develop the dynamical theory of heat." End quote. At the Second International Electrical Congress, on 31st August 1889, the joule was officially adopted alongside the watt and the quadrant, later renamed to Henry. Joule died in the same year, on 11th October 1889. At the Fourth Congress, 1893, the International Ampere and International Ohm were defined, with slight changes in the specifications for their measurement, with the International Joule being the unit derived from them. In 1935, the International Electrotechnical Commission, as the successor organization of the International Electrical Congress, adopted the Georgi system, which, by virtue of assuming a defined value for the magnetic constant, also implied a redefinition of the joule. The Georgi system was approved by the International Committee for Weights and Measures in 1946. The joule was now no longer defined based on electromagnetic units, but instead as the unit of work performed by 1 unit of force, at the time not yet named Newton, over the distance of 1 meter. The joule was explicitly intended as the unit of energy to be used in both electromagnetic and mechanical contexts. The ratification of the definition at the 9th General Conference on Weights and Measures in 1948 added the specification that the joule was also to be preferred as the unit of heat in the context of calorimetry, thereby officially deprecating the use of the calorie. This definition was the direct precursor of the joule as adopted in the modern International System of Units in 1960. The definition of the joule as joule equals kilograms times meters squared per second squared has remained unchanged since 1946, but the joule as a derived unit has inherited changes in the definitions of the second in 1960 and 1967, the meter in 1983, and the kilogram in 2019. Practical examples. 1 joule represents, approximately, the amount of electricity required to run a 1 watt device for 1 second, the energy required to accelerate a 1 kilogram mass at 1 meters per second squared through a distance of 1 meter, the kinetic energy of a 2 kilogram mass traveling at 1 meter per second, or a 1 kilogram mass traveling at 1.41 meters per second, The energy required to lift an apple up 1 meter, assuming the apple has a mass of 101.97 grams. The heat required to raise the temperature of 0.239 grams of water from 0 degrees Celsius to 1 degree Celsius. The typical energy released as heat by a person at rest every 1/60th of a second, or 17 milliseconds. The kinetic energy of a 50 kilogram human moving very slowly, 0.2 meters per second, or 0.72 kilometers per hour. The kinetic energy of a 56 gram tennis ball moving at 6 meters per second, or 22 kilometers per hour. The food energy, kilocalories, in slightly more than half of an ordinary sized sugar crystal, at 0.102 milligrams per crystal. Multiples. SI multiples of Joule. 10 to the negative 1th, decijoule. 10 to the negative 2, centijoule. 10 to the negative 3, millijoule. 10 to the negative 6th, microjoule. 10 to the negative 9, nanojoule. 10 to the negative 12, picojoule. 10 to the negative 15th, femtojoule. 10 to the negative 18th, attojoule. 10 to the negative 21st, zeptojoule. 10 to the negative 24th, yoctojoule. 10 to the negative 27th, rontojoule. And 10 to the negative 30th, quectojoule. Going up, 10 to the 1st, decajoule. 10 to the 2nd, hectojoule. 10 to the 3rd, kilojoule. 10 to the 6th, megajoule. 10 to the 9th, gigajoule. 10 to the 12th, terajoule. 10 to the 15th, petajoule. 10 to the 18th, exajoule. 10 to the 21st, zettajoule. 10 to the 24th, yottajoule. 10 to the 27th, ronajoule. And 10 to the 30th, quetajoule. Zeptojoule. 160 zeptojoules is about 1 electron volt. The minimal energy needed to change a bit of data in computation at around room temperature, approximately 2.75 zeptojoules, is given by the Landauer limit. Nanojoule. 160 nanojoules is about the kinetic energy of a flying mosquito. Microjoule. The Large Hadron Collider produces collisions of the microjoule order, 7 TeV, per particle. Kilojoule. Nutritional food labels in most countries express energy in kilojoules. 1 square meter of the Earth receives about 1.4 kilojoules of solar radiation every second in full daylight. A human in a sprint has approximately 3 kilojoules of kinetic energy, while a cheetah in a 122 kilometers per hour sprint has approximately 20 kilojoules. 1 watt-hour of electricity is 3.6 kilojoules. Megajoule. The megajoule is approximately the kinetic energy of a 1 megagram ton vehicle moving at 161 kilometers per hour, 100 miles per hour. The energy required to heat 10 liters of liquid water at constant pressure from 0 degrees Celsius to 100 degrees Celsius is approximately 4.2 megajoules. 1 kilowatt hour of electricity is 3.6 megajoules. Gigajoule. 6 gigajoule is about the chemical energy of combusting 1 barrel of petroleum. 2 gigajoules is about the Planck energy unit. 1 megawatt hour of electricity is 3.6 gigajoules. Terajoule. The terajoule is about 0.278 gigawatt hours, which is often used in energy tables. About 63 terajoules of energy was released by Little Boy. The International Space Station, with a mass of approximately 450 megagrams and orbital velocity of 7,700 meters per second, has a kinetic energy of roughly 13 terajoules. In 2017, Hurricane Irma was estimated to have a peak wind energy of 112 terajoules. 1 gigawatt hour of electricity is 3.6 terajoules. Petajoule. 210 petajoule is about 50 megatons of TNT, which is the amount of energy released by the Tsar Bomba, the largest man-made explosion ever. 1 terawatt hour of electricity is 3.6 petajoules. Exajoule. The 2011 Tohoku earthquake and tsunami in Japan had 1.41 exajoules of energy, according to its rating of 9.0 on the moment magnitude scale. Yearly U.S. energy consumption amounts to roughly 94 exajoules, and the world final energy consumption was 439 exajoules in 2021. 1 petawatt hour of electricity is 3.6 exajoules. Zettajoule. The zettajoule is somewhat more than the amount of energy required to heat the Baltic Sea by 1 degree Celsius, assuming properties similar to those of pure water. Human annual world energy consumption is approximately 0.5 zettajoules. The energy to raise the temperature of Earth's atmosphere 1 degree Celsius is approximately 2.2 zettajoules. And yottajoule. The yottajoule is a little less energy than the amount of energy required to heat the Indian Ocean by 1 degree Celsius, assuming properties similar to those of pure water. The thermal output of the sun is approximately 400 yottajoules per second. Conversions. 1 joule is equal to approximately, unless otherwise stated, 10 to the 7th erg, exactly, 6.241 times 10 to the 18th eV, 0.239 calories, 2.39 times 10 to the negative 4th kilocalories, 9.4782 times 10 to the negative 4th BTU, 0.7376 foot-pounds, 23.7 foot-poundals, 2.7778 times 10 to the negative 7th kilowatt-hours, 2.7778 times 10 to the negative 4th watt-hours, 9.8692 times 10 to the negative 3 liter atmospheres, 11.1265 times 10 to the negative 5th grams speed of light squared. Units defined exactly in terms of the joule include 1 thermochemical calorie is 4.184 joules, 1 international table calorie is 4.1868 joules, 1 watt-hour is 3600 joules, 1 kilowatt-hour is 3.6 times 10 to the 6 joules, 1 watt-second is 1 joule, 1 ton of TNT is 4.184 gigajoules, and 1 Fo is 10 to the 44th joules. Newton meter and torque. In mechanics, the concept of force, in some direction, has a close analog in the concept of torque, about some angle. A result of this similarity is that the SI unit for torque is the Newton meter, which works out algebraically to have the same dimensions as the joule, but they are not interchangeable. The General Conference on Weights and Measures has given the unit of energy the name joule, but has not given the unit of torque any special name, hence it is implied the Newton meter, a compound name derived from its constituent parts. The use of Newton meters for torque but joules for energy is helpful to avoid misunderstandings and miscommunication. The distinction may be seen also in the fact that energy is a scalar quantity, the dot product of a force vector and a displacement vector. By contrast, torque is a vector, the cross product of a force vector and a distance vector. Torque and energy are related to one another by the equation E equals tau theta, where E is energy, tau is the vector magnitude of torque, and theta is the angle swept in radians. Since plane angles are dimensionless, it follows that torque and energy have the same dimensions. Watt-second. A watt-second, symbol Ws or W times S, is a derived unit of energy equivalent to the joule. The watt-second is the energy equivalent to the power of 1 watt sustained for 1 second. While the watt-second is equivalent to the joule in both units and meaning, there are some contexts in which the term watt-second is used instead of joule, such as in rating of photographic electronic flash units.